Hello, welcome. Thank you for joining me once again, where today we're feeling particularly orange-pilled. So we are. Say no more. There's the code for those of you that are watching this for free. Right. Yes, some of you will get to see this for free. This is the last of the lessons in my How to Read the Science Competently series of instructional videos that I'm going to release for public view at any time to any number of people. All the rest of this course is available by subscription only on the Patreon service, which is BART_KAY at Patreon. When you go to Patreon, that's what you put in. Yeah, that. Okay, so what is the lesson today? The lesson today is the standard error and significance when we find these things in studies. Alrighty. All of that there, the BTEO, all of that means by the end of this discussion you will be able to. It's basically another way of saying here's the learning outcomes. By the end of this discussion you will be able to. Alright, it's instruction. It's compulsory. First of all, you will be able to broadly describe the normal or bell-shaped curve. There you go. Learning outcome 1 taken care of. Now stick around, we'll give it a bit more than that. Conceptually explain what is the standard deviation. All right, so that's number 2. Stick around for that till the end. Conceptually explain what the standard error is, as opposed to the standard deviation. You will be able to state that the T statistic determines the acceptance or rejection of intergroup mean differences in statistics. You will further be able to state that the standard error is a mathematical determinant of the T statistic. That's the denominator, in fact. And therefore you will be able to broadly discuss the difference between statistical significance and clinical significance in a sensible way, in a discussion, exchange, or educational situation as it may be, as regards all of that. So, if that was a problem for you, stick around till the end and it won't be any more. That's the plan anyway. Right, let's describe this bell-shaped curve thing. A bell-shaped or normal curve, sometimes called a Gaussian curve, is what you will get if you measure almost any physiological response in a living being as regards a given variable, the blood pressure, the height in centimetres, any continuous variable measurable on a human being. If you measure a bunch of human beings and those human beings are randomly selected from the population concerned, so that's the first assumption, okay? We have to assume that the population that has been selected from the main population to which it's supposed to be able to be paste-backable needs to be appropriate, all right? Usually a problem in studies, but anyway, there it is. You get a proper random sample out of a given population. You test them for something physiological. You will get a bell-shaped curve in terms of the data points on an XY graph of that particular thing, such that most of the numbers will fall one side or the other of the mean value, the middle value, and X amount will not. Basically, it gives you an idea of the spread of the data around the mean. And you will find that most of the data is around the mean, and the further away from the mean value you get, the less number of representations in that data set there were. The second assumption of the bell-shaped curve is that your sample size is large enough from your population that you have selected that you will actually get the curve. It will fill out because you need a certain sample size to ensure that you're going to get a curve which describes the population broadly. Okay? So that's basically what the bell-shaped curve looks like. How is it used? It's used to form the basis of assumptions that I'll flesh out a bit more fully. Don't panic. I know about the standard error. I know about the t-test. I'm going to get to that. All right? Don't panic. I want to give you the concept here of how the normal shaped curve is used to make assertions in science. Okay? Let's say we have two samples, randomly selected, just genuinely randomly sampled, select members of a given population at large, two individual pools of sample size n equals whatever it is. Population A, population B from total overall population X, Y, or Z. Okay. We measure each of those populations for their height in centimetres. Group A has a mean and bell-shaped curve that looks like the one drawn there on the left, behind the one on the right in front. And the one on the right is the other group. So we've measured it twice and that there's a difference. Okay? In that mean value from each of those groups. For whatever reason, be that to do with a properly disciplined experimental protocol whereby everything was controlled such that we can suggest we have a cause and effect relationship here. Just the statistical inference. That mean value differs from the other one. What I've done here is I've overlapped these by a degree where 95-ish% of the data in the group on the right falls to the right of the mean value of the group on the left, and 5% does not. From that, I know about the t-test and standard errors. Don't panic. From that, it's asserted in the scientific literature that those two groups are statistically different, which is parsimonious. Actually, what they should say is the likelihood, still parsimonious, but less so, the likelihood that the value of group A is different from the value of group B, the likelihood of that difference being due to dumb chance is about 5%. It's 95% certain to do with whatever experiment that we've undertaken. Pretty much. P equals less than 0.05. There we go. Job's done. Pat ourselves on the back. Publish it in the literature. Write it in our CVs. Look, I published this fine article here that proved absolutely something. We'll get to that at the end. That's the bit you need to stick around for, the actual conclusions of this, because it's not what you expect, those of you that have had some exposure to stats already, I promise. All right? So, that's ostensibly what's done in science when you're taking two groups, two populations, you're subjecting one group to an experimental protocol and you're controlling the other group. The actual statistical assertion here I need to flesh out, because what I've said to you is conceptually what is done, but not actually what is done computationally. There are some very big differences, and they're important. So let's do that. Stick around, it's worth it. The standard error, you need to understand what it is. When I said I'd put 95% or so of the data in the group on the right to the left of the mean value of the group data of the group on the left, I had to use a standard deviation graphically, visually, to estimate where that is, to place these correctly on this chart as such, or near. I didn't get it quite right, but it's near. All right? The standard deviation are those vertical lines, and you'll see that one standard deviation either side of the mean is in yellow, and that's 68% of all of the data. It's most of the data up the middle of the chart. in both groups. Okay? Between the first and second standard deviation, that will take you up to 95% of the data. And that's in a lightish orange colour. And then outside two standard deviations, you've got 99.97% of all the data represented. So what I'm saying is that the prevalence of data outside that main 68% clump is progressively less and less. All right, that's what the standard deviation is. There's a whole bunch of math involving a bunch of calculations that you really don't need to know how to do to work out what the standard deviation of any given Gaussian distribution or bell-shaped curve data set is. You don't need to know it. You just need to know that you can get it out of just about any computer program, like Excel. You can get it out of Excel easily enough by just putting in a function. Work out the standard deviation for me. Oof, there it is. All right. So what I'm showing you conceptually here is if we were to determine that Group A is definitely different from Group B, 95% sure, not due to dumb chance, okay, what we're making an assertion there is on the basis of these people, those people in Group A and those people in Group B. They have quite a wide standard deviation usually in terms of the variability around the mean or the slope of the curves, if you want to think of it that way. It's quite flat in most physiological measurements. There is a lot of noise around the signal being the mean value, the absolute peak top of each of those bell-shaped curves. So when we are looking at doing research with widely variable data sets like physiological parameters, we do some statistical smoke and mirrors. Ooh, that's what we do. And what we're going to do now is we're going to use a thing called a standard error. This calculation abandons any claim about the difference between Group A, these people, and Group B, those people. It abandons that because it narrows down the standard deviation in effect. How is that done? The standard deviation, those measurements, are divided by the square root of the number of data points in each data set, or in that data set, I should say. The bigger your sample size, the smaller the standard deviations are going to be, the standard errors, the adjusted standard errors are going to be. So in order to get an idea of the noise around a signal as reported in a study back to you, that's based on a standard error, we have to multiply that standard error by the square of n to get an idea of how much overlap of those two data sets there really was, how much spread was there really around that. Because a nice peak-sided bell-shaped curve, that's not what you usually get for physiological measurements. Cowpat-shaped pie is what you normally get. Note to self to mention, yes, I do understand also, those of you that have had some exposure, that there's another statistic called the standard error of the difference, which gives you an idea of the gap itself rather than looking at the two groups discretely and saying, is this group different from that group? It's just saying, look, is the difference real? It's another way of going around basically asserting the same thing really. And it takes the standard error of the difference of each of the curves into consideration separately because they can vary from one another as well, and it's a bit better. Fine. But you don't need to know that. Ignore that last bit if that was whatever. Okay. What does this then assert? What is the implication if you say one group is different from another group based on a standard error? You're saying it statistically, not that these actual people are different from any other actual people. It's usually a very, very small change because of the tiny, tiny squashing in of the standard deviations that occurs with larger sample sizes. But actually, it completely obfuscates the fact that there is so much swampy noise around that signal in those studies that it's laughable. And as such, the statistical power, which I'll cover in a different lesson, is not up to snuff for any decent journal or any true connoisseur of the actual science. All right? What does it actually assert? Was the question. Answer the question, son. Right, here it is. What does it actually assert? If I take a random sample from the overall population X, Y, or Z, group A, I will get a mean, a bell-shaped curve, and a standard deviation within that curve for that group A. If I take a group B at random, and I do not intervene in any way, I will get a slightly different mean and a slightly different standard deviation. It will be slightly different placed in absolute terms. If I then take a group C without intervening in any way, I'll get a slightly different result again. Group D, E, F, G, as many as you like, stack them up, and what you will end up with is a very tight bell-shaped curve with very small standard deviations of what the means of those groups were, despite the fact that the standard deviation around all of those data sets was so wide that you've got so much crossover that what you've got is noise and not signal. I hope this is going up some flagpoles. The t-test is the statistic that is reported that suggests that experimental group is different from another group. This t-test I've given you here is the test that asserts whether this particular group A is different from what we would expect from the total population concerned, all people. For example, assumption of the t-test. The mean value of all people is known. Why is that an assumption? Because it's in the equation. You need to know the value to calculate it. It's a determinant value in this computation. So you have to have measured everybody in the population. There are different forms of the t-test that assert group A is different from group B rather than anything to do with the grander population at large. So again, if you use it, that precludes you talking about the general population, doesn't it? Sorry about that logic. Not sorry. Okay. The t-test takes X with a bar over the top of it. That's the mean value from the experimental group that you've selected and you've done an intervention. Bam. You know the value from the general population somehow, magically. And here's your result that you got because you gave them a drug that you don't want to test against no drug because that's not ethical or something. Okay? We take all of that, we take that mean value, we take off what the population value that we magically know is somehow, and we divide all of that by the standard deviation divided by the square root of n. The standard deviation is equal to the square root of n. We've just taken that and put it on the denominator of this sum. So, what is the implication? That we can logically, validly, correctly make and be seen to be someone with robust discipline around their conclusion making. Here is the ramification of the t-test. The experimental group in our investigation, or as compared to a population mean, somehow that we know, that value that we've got here in this group of people differs from what we would have expected, and the probability that that chance, that level of separation, has come from dumb chance of correct random sampling is whatever the probability statistic says. We usually go for p is less than 0.05 for statistical significance by convention. So that's the conclusion. This value that we have here in this group of people that were measured on this occasion under those circumstances at that time, the mean value we got there, never mind the spread of it, ignore that for some reason, but the mean value we got, the average value, is different from the one that we would have expected statistically, and the chance that we got that wider difference that we did get is less than our pre-selected value at which we would accept that hypothesis at p is less than 0.05. Okay. Does it say anything about cause? Nope. Does it say anything about effect? Only if you've got a cause. Show me an experiment that establishes cause. Does it prove, absolutely prove, anything? Nope, doesn't claim to either. Only people that don't understand science and how to read it claim that. Research here absolutely proves that. Does it show that whatever we gave these people had an effect on their blood pressure, if that's what we measured? Nope. Does not. All right, there it is. I hope you've enjoyed this week's lesson. A little bit mathematically and statistically. I'll be interspersing the math and the logic and the discipline of the epistemology, etc., with more discursive looks into other bits and bobs, as I have been doing up to this point so far in the course. This is the first actual, here are some maths, here are some statistics. How did you like it, getting your toe in the water? Was it warm and inviting, or did you find that a bit cold and prickly in some way? Give me some feedback, I'd love it. All right, there it is. Pretty much that's all I needed to say today. Yeah. Hope you're following along. Hope you're enjoying it so far. Stick around. There'll be much more before the course is finished when I get around to doing the videos, which I'm trying to do on a relatively as near to weekly as I can do. I can't guarantee it. There are a lot of other things on, but I'm definitely trying. Ask my mum. She'll tell you how trying I am. Anyway, see you next time when we'll talk about something else. Ciao for now.